Hello everyone. So, we will continue with the extreme cold protective clothing. So, while used in extreme cold condition, there are different situations where are actually coming to come across. So, this situation, one of them wind chill effect, where the wind at high velocity blows and that sometime takes away the heat in convective mode, forced convective mode. So, the experimental study which has been carried out here it has been studied the impact of layer thickness and impact of different convective modes, normal convective mode and forced convective mode and also non-convective mode. So, these modes of heat transmission we have studied. There are three layers as we have already discussed: outer layer, middle layer and inner layer, and between layers the air gaps were created. Between middle layer and outer layer air gap was created, and between inner and middle layer air gaps were created using the metallic frame, where the air gap thickness between layers were this varied. This air gap thickness between outer and middle and inner layers were varied. These are the different air gap combinations. So, 0 thickness means there is no air gap, extra air gap, they are in contact, these two layers are in contact with each other. So, 0 air gap means the total thickness of ensemble will be the actual thickness of the addition of this actual thickness of the fabrics. So, gradually the air gap thicknesses were changed, and that means, so second combination if we see here, additional air gap of 2 millimeter between middle and outer layer was created, and where the 0 air gap between inner and middle layer. So, total thickness would be thicknesses of 3 layers plus 2 millimeter of air gap. In this way we have created large number of combinations here, and the fabric variabilities are: the inner layer we have taken woven fabric which is constant for all the layers, and in middle layer what was created, the fabrics with higher air pockets. These fabrics with higher air pockets were taken. So, non-woven waddings were used in sample A1 and A2 in middle layer. In rest 3 samples A3, A4, A5 warp knitted fabrics were used, the spacer fabrics were used, and the outer layers were mainly woven fabric for A1, A2, A3, and for A4 and A5 the knitted fabrics were used which were coated. So, for A4 it was breathable coated, and A5 it was wave knitted aluminum coated. So, these 5 combinations were taken for different modes of convective heat transmission. The heat transmission was assessed using guarded hot plate. This is the guarded hot plate system, where its bottom plate, test plate, guard plate and fabric specimen, and 3 modes of convective heat transmissions were created. One is non-convective mode, natural convection and forced convection. If we do not want any heat to be transmitted through convection, if we want to stop convection, so we can use a top plate here. So, there it will stop the heat transmission through transmission of medium, like air movement is being stopped here. So, in this mode only heat will get transmitted through conduction and radiation. If we want natural convection, so we will remove the plate, the heat will get transmitted through conduction, radiation as well as natural convection. Due to the natural convection, it was expected that the fabric will have higher thermal transmission. A third mode of convection was forced convection, where top plate was removed and extra air was blown along the plane, so that it takes away additional heat which normally we encounter during application in windy condition. So, if we see here the fabric assembly 1 and assembly 2, where we have seen the outer layer was normal oven fabric with pores present. As we increase the total thickness of fabric, this ensemble increase in thickness means the increase in only air gap, because the combinations are same for say assembly 1, inner layer was oven fabric, middle layer non oven and outer layer again oven fabric. Keeping the same combination of fabrics, only we changed the air gap. So, total thickness it is up to say 17 millimeter. So, as we increase the thickness of ensemble, total assembly 3 layer assembly along with the thickness. So, as we increase the thickness means we are incorporating extra steel air. So, thermal resistance of the ensemble increases. When we compare the convective mode for a particular thickness, say at thickness 10, if we compare, the thermal resistance for non-convective mode is highest, followed by natural convection. Between non-convection and natural convection, so only difference is that the transmission of heat in case of non-convection, it took place due to radiation and conduction. When we allow the natural convection, additional heat was transmitted, that is why resistance reduces. But in case of forced convection, if you see, the thermal resistance has dropped drastically. This is the thermal resistance. This is due to the fact that the pores present in the outer layer, that is oven fabric, which has helped to extra heat transmission through forced convection. So, that is why you can see the thermal resistance has dropped significantly, and the same phenomena was there for all other thicknesses. For all the air gaps, the exactly same phenomena was observed. The same trend was observed with the fabric assembly 2. Now, if we see the fabric assembly 4 and 5, the trends are same with the thickness. With the increase in thickness, the thermal resistance increases, but as far as convective modes are concerned, the forced convection, the heat loss due to forced convection has reduced to a great extent. So, that means the resistance has increased, that which shows for fabric assembly 4 and 5 there were least forced convection or forced convection was absent. This is mainly due to the fact that breathable and metallic coated fabric improves the thermal insulation property at forced convective mode, shows that in case of windy condition we must use coated or laminated outer layer fabric just to reduce the forced convection. Now, fabric assembly 3, if we see, go back to earlier, this is the fabric assembly 3 and fabric assembly 1. If we compare these two, everything remains same, only the middle layer was used warp knitted spacer fabric, and fabric 1 it was non-woven wadding. Now, fabric 3 and fabric 1, if we compare, higher thermal resistance for non-woven fabric, which is more than spacer assembly. This is the thermal resistance of assembly 3 with the spacer fabric and overall thermal resistance of fabric assembly with non-woven fabric. So, non-woven has got higher thermal resistance than spacer fabric, that is mainly due to the alignment of fibers. Although spacer fabric has got very high air entrapment, but the space between two layers, inner and outer layer, two layer, the air is actually air movement can take place freely. So, that helped in natural convection within that structure, and also the radiative heat transmission through air is higher than the through fiber. So, nonwoven fabric, it blocked the fibers blocked the radiative heat transmission. So, overall thermal resistance in nonwoven is higher than the spacer fabrics. That means, it is recommended to use nonwoven fabric instead of spacer fabric, and also the outer layer needs to be coated, breathable coated when we use for the high wind condition. There are different parameters which control the thermal resistance or thermal transmission characteristics. So, next study is carried out on needle punched fabric, because needle punched nonwoven fabric is used in middle layer mainly for thermal insulation purpose. The aerial density was varied with 100, 200, 300 grams per square meter. Punch density, punches per square centimeter was varied 50, 103, 210, and depth of needle penetration 5, 10 and 15. So, punch density and depth of penetration, it is basically it makes the fabric compact, keeping the mass per unit area constant, keeping the actual material constant. It increases the compactness of nonwoven fabric. In this study, polyester fiber of 1.5 denier with 32 millimeter length was used. Box and Banken experimental design was applied. So, guarded hot plate was used for evaluating the thermal transmission characteristics. So, this is the sweating guarded hot plate, where we can measure the evaporative resistance also. Now, looking at this diagram, we can see as we increase the fabric mass per unit area, it reduces the air permeability. So, it due to presence of more and more number of fibers, it reduces the air permeability, but punch density and depth of needle penetration does not have significant effect on air permeability. Increase in mass per unit area, it increases thermal and evaporative resistance also. So, thermal resistance, so with the increase in mass per unit area, thermal resistance increases, but with the increase in punch density, although there is no effect on air permeability, it reduces thermal and evaporative resistance. Similar effect was observed due to depth of penetration, it reduces thermal and evaporative resistance. And as we see, the increase in mass per unit area or increase in punch density, it reduces the thermal resistance. If we increase the punch density, this is due to the fact that as the punch density increases, the fabric becomes more and more compact, the air pockets inside the structure reduces. So, the thermal resistance also reduces. Now, in the outer layer, if we add inner layer and outer layer, so inner layer was used knitted fabric and outer layer PTFE coated fabric was used with the nonwoven fabric, and this is showing the nonwoven fabric with the blue line and the red line showing the multi-layer combination. So, and this diagram is showing the thermal resistance, and in right side it is showing the evaporative resistance. If we see that introduction or addition of inner and outer layer with the nonwoven marginally influence the thermal resistance, marginally thermal resistance has increased. That means, the nonwoven is performing mainly insulating function, the inner and outer layers are not adding the insulation too much. As far as evaporative resistance is concerned, addition of the outer layer which is coated fabric increases the evaporative resistance significantly. So, this we should be very careful, the evaporative resistance should not increase too much. Now, if we see the total overall trend, as the depth of penetration increases, the thickness of nonwoven fabric reduces. Similar trend is observed with the punch density, and mass per unit area as it is increasing, the thickness also increases, but increase in thickness is not that proportion, because with the increase in mass per unit area, the fabric compactness, overall density of fabric also increases due to more and more entanglement. So, that is why the thickness, although it is increasing, but not with that proportion. As the depth of penetration increases, depth of penetration and punch density, it has least effect on air permeability, but fabric mass per unit area has got great effect. As the mass per unit area increases, air permeability reduces. So, with the increase in depth of penetration, the thermal resistance reduces, as I have mentioned, the fabric becomes compact. So, this is true for punch density, needle punching density also, but if you see the trend for fabric mass per unit area, initially with the increase in mass per unit area, the thermal resistance increases, because with the increase in mass per unit area means more and more fibers are there for resistance, but after reaching certain point the thermal resistance drops. This is mainly due to the fact that at this point more fibers are there, more entanglements will be there, and fabric density, the air pockets within the fabric will be less. So, that the air which is very highly insulating, if less quantity of air is there, that means overall thermal resistance of the fabric structure will drop. So, with the increase in depth of penetration and needle punch density, evaporative resistance also reduces, and with the increase in fabric mass, the evaporative resistance increases. So, these are the overall trends. Another problem while using the extreme cold protective clothing is that resilience property. During use, the bulky middle layer sometime gets compacted. So, during compression, the air, entrapped air comes out. So, it is very interesting to understand the effect of compression on thermal resistance of fabric. So, one instrument has been designed and developed where the thermal resistance can be measured under different compression level. So, this is the instrument where the guarded hot plate was used, but it is in inverted manner. So, guarded hot plate, the principle is that, let me explain. The main problem with control the heat flow direction. So, we can control the air flow direction by channel. So, by this channel, so we can control the air flow direction. We know the air is flowing from this portion to this portion. Even for liquid also, that we can measure the air flow, any fluid, liquid or air flow, we can measure the quantity of fluid flowing through this pipe at certain time. So, in that case we can calculate the flow rate, but the main problem with heat is that, suppose this is heater, and if we heat, we cannot control the heat in one direction. Here it can be controlled, so that we can, if we want to measure the flow rate through the fabric. So, air flow rate through air permeability we measure like this, we will put the fabric sample here and we will measure the air flow rate, air quantity of air flowing through the fabric very easily under certain pressure. But as far as heat transmission is concerned, this is heater. If we place fabric on it and the heater is on, it is actually generating heat. It is very difficult to measure that how much quantity of heat is passing through the fabric, because the heater will try to dissipate heat in different directions. So, quantification of proportion of heat through the fabric is very difficult, it is not known. So, that is why by this process it is not possible to measure the thermal transmission. So, we have to devise the technique. So, that is why guarded hot plate system was developed. Here this is the heater, okay. This is called test plate, and it is connected with the heater 1. Now, to prevent the heat flowing in other direction sideward, we want the heat to be flown only in this direction, and we want to measure this heat. This is the fabric sample through the fabric specimen, this is what we want. Now, to prevent the heat to flow sideway direction, one insulating material is placed here. This is the insulator. So, cork is a very good insulator is placed, and also another ring was used. So, this is the guard ring of metal. So, if I draw the top view, this is the top plate, these are the insulating cork, insulating material to prevent the heat flow, and another ring, this is a guard ring, metallic guard ring. So, this guard ring is again heated with H2 heater 2 to keep the temperature same as that of test plate. So, typically the 37 degree Celsius temperature is kept, here also 37 degree Celsius is kept. The reason is that to maintain the same temperature, so that there is no temperature gradient, the heat will not flow sideway. To stop the heat flow from the sideway, we add one guard ring. So, heat can flow only in this direction, but it can also flow in the bottom direction. So, to prevent the heat flow again on the bottom direction through the bottom. So, here another plate was used, this is actually H3, that is bottom plate is used, and here again temperature is kept say 37 degrees Celsius. So, there is no temperature gradient, heat will not flow in this direction. So, heat will only flow through the fabric specimen. So, in this way we can guard the heat to flow from other directions, and the actual data of the power required by test plate, that is H1 heater, is used to calculate the heat flow rate through fabrics. So, whatever I have explained, let us see through animation here. In the case of test plate, only test plate, this is top view, this is side view. Now, we are putting fabric on that, on test plate, and test plate is connected with the heater. That is a heater and a power supply. Basically, it is a power supply test. Now, heat is flowing in all the directions. So, we do not have any control. Now, in guarded hot plate method, the test plate, this is the insulating material, guard plate, this is guard plate and bottom plate red one, and fabric is placed on that, and this all three plates are connected with the power supply, and here heat is only flowing through the fabric, the heat from the test plate. So, we can measure. So, by knowing the power requirement and area and temperature difference. So, this is the way we can measure the thermal conductivity. A similar technique was adopted here, but the bottom plate earlier it is placed at the top. This is the actual test plate and these are the guard rings, guard plate, and the support plate here which is perforated one, and over this bottom plate here the fabric is placed, and total this guard ring assembly is connected with a traverse arrangement where the pressure is applied on the fabric, and this when it is moving down the fabric gets compressed, and we can measure the compression as well as thermal transmission. The heat flows from the test plate by conduction, convection, radiation. The measuring head pressure 5 to 30 gram per square meter square centimeter. So, resistance can be measured here, and also we can get the forced convection here by blowing fan, and this bottom plate is perforated, that will help in the convective forced convection. This is the system, this is the photograph of the system. The total guard plate system is, this is the load cell, this is the total guard plate system and perforated bottom plate here, and fabric sample is placed here. So, we can get load versus thickness curve as well as at different compression level we can calculate the thermal transmission. So, this is the data we get from the instrument. Now, the data from this instrument was compared with other standard instruments like sweating guarded hot plate, Alambata is another instrument for measuring the thermal transmission, and this developed instrument, and this instrument the minimum pressure available is the 700 Pascal. The thermal resistance of the fabrics, there are different 20 different fabrics were tested just to understand whether the instrument is giving consistent result. Looking at the trends, it is clear that the developed system, developed instrument is giving similar trend as far as thermal properties are concerned, but the thermal resistance value it is lower than the sweating guarded hot plate as well as the Alambata. The main difference between these three instruments are sweating guarded hot plate, the pressure applied almost there is no pressure applied on the fabric. In Alambata we need minimum pressure, and minimum pressure is highest here in the developed instrument. So, highest pressure, that is 700 Pascal pressure is required, and this trend it shows that as the compressional load increases the thermal resistance decrease. So, for any fabric, so this is the curve for 7 gram per square centimeter pressure. This is for 14, 21. So, as we keep on increasing the pressure, so fabric gets compressed, the reduction in thermal resistance is 45%, 70% and 80%. So, in 7, 14 and 21 gram per centimeter square compressional load, 45%, 70% and 80% reduction in thermal resistance with respect to thermal resistance measured by Allam-Bata. So, that has been observed here. Next experiment was the wear trial technique. So, actually the fabrics were, the outer wear, the jackets were prepared and the experiment was carried out in cold chamber. So, 4 jackets were developed. So, jacket 1, the middle layer was needle punched fabric. A typical, the mass of jacket was around 800 to 864, within that range. Here inner and outer layer were kept constant for all the 4 jackets. So, jacket 2 through air bonded fabric where thickness was very high, and this through air bonded fabric, once it was measured in isolation, this through air bonded fabric was having highest thermal insulation, and jacket 3 was needle punched hollow fiber with 6 denier hollow fiber, and jacket 4 was needle punched 15 denier hollow fiber. So, these 4 fabrics were used, 4 non-woven fabrics were used, and the experiment was carried out at 3 different temperatures, 10 degree Celsius, 0 degree Celsius and minus 10 degree Celsius. Along with the jacket, there are other components were used, and these components were used constant for all the jackets. So, relative humidity at the skin and temperature at the skin at different body parts were measured. This is the test condition. Total test time was 80 minutes, the test protocol here, and the subjective assessment was carried out. These are the test setup, and climatic chamber was there. So, after wearing this jacket, the person entered into the climatic chamber. Now, if we see the temperature at the skin for jacket 2, the temperature at the skin was lowest. Okay. This is temperature is lowest temperature, for other this is much high. So, jacket 2 was actually produced through air bonded fabric. On the other hand, if you see the humidity is maximum. So, the person was feeling cooler due to higher humidity and temperature was low. Although this jacket 2, which is made from through air bonded, it was having very high insulation, but once it is coming to the jacket, due to higher heat, the sweating was there. This is due to sweating, high humidity, and that resulted the cooling of the at the skin. So, high humidity is generated, and this high humidity is also due to the fact that due to high thickness, very high thickness of through air bonded, the moisture transmission was not proper. At 0 degree Celsius, these are the trends, but if we see minus 10 degree Celsius, again the temperature at the skin was lowest for through air bonded fabric at different region of the body. But once we see the humidity, again at minus 10 degree Celsius, the layer with very high thermal insulation, it is giving highest humidity at the skin, because the through air bonded fabric again its thickness is very high. So, the moisture vapor transmission does not take place at that rate. So, the conclusion here is that the produced jacket, although worked well at cold condition, it was found that the jackets which has maximum thermal insulation, that is jacket 2 for example, performed poorly due to excessive sweating. The accumulation of sweat and its inability to transfer the sweat to the atmosphere due to high thickness of the fabric ensemble. So, once we try to develop the fabric ensemble for the extreme cold climate clothing, we must take into consideration the total thickness of insulating layer. The thickness should not be too high, which will prevent easy flow of the humidity. So, we will end here the extreme cold protective clothing. In next class, we will start with a new topic. Till then, thank you.